repeaters, photonic devices, and station distributed from different countries on a large distance spanning hundreds of kilometers, developing world's first graphical quantum internet application. That project is part of a big undertaking as a part of the European Union within the quantum flagship. But for many of you, these concepts are new, working in the US. So let's bit of a background about what's actually these cryptic means, these cryptic names mean. So the background story is as follows. In 2017, a couple of big institutes, research institutes from Europe specializing in quantum networking and computing, like QTech. QTech is a department within Delft University of Technology, focusing primarily on anything related to quantum systems. ICFO is a Spanish institute of working on, among many other things, quantum systems. University of Innsbruck, Paris Center for Quantum Computing, joined forces to create the quantum internet development. So the photo that you see was a signing moment of the memorandum of understanding. Then in 2019, the Quantum Internet Alliance has been selected to become part of the bigger undertaking within the European Quantum Flagship. What are quantum flagships? These are the core strategic research domains and research topics sponsored directly by the European Commission. And one of them is actually quantum internet. So this is a part of a big project from the Tron until 2022. And from 2022, from the end of the quantum flagship, another initiative started, also supported by the European Commission, with the aim of developing quantum internet made in Europe, with the aim of having a first practical demonstration of the quantum internet by 2029. So keep fingers crossed that actually it's going to be an actual realization of that project. So who are part of the quantum internet alliance and quantum flagship? Many universities, many research and technology organizations, industry players, quantum startups, and many other smaller organizations. France, the Netherlands, Germany, many of the logos you see here are actually pretty well to you. Some of them are less known. But as you see, they're coming from a different walks of life, different backgrounds. All of them trying to capitalize, like this, understand, and contribute to the knowledge of developing on that platform. Not purely from a physical point of view, but mostly also, please bear in mind, from the application perspective. So in the previous project, before the Quantum Internet Alliance, we had, for example, many banks that wanted to use the quantum systems for super secure quantum communication support by quantum systems. So focus on diversity, full stack solutions on different types of products and quantums. So I'll talk about for the rest of the presentation in a very high levels, because we had a lot of deep technical discussion. I hope that this presentation will be slightly more enjoyable in a way. But we'll talk about our research, last research result, which was published in Nature just a few, I would say, weeks ago, in which we are presenting world's first operating system for executing quantum applications on the quantum network nodes. And that's what we're talking about. And as you see, that my name is literally almost at the end of the project, because you see that less than people working on this project was pretty large. This project was more than 6 years in the making, involved with lots of ups and downs. So if you want to hear about some interesting funny anecdotes about this project, you can just leave it to the end of the.
He said order.
That order took a lot of effort to reach, right? So Carlo was a PhD student that I supervised together with Stefan Berner. So my background, as you probably know, is coming from a telecom. So I did my PhD in telecommunications. So with my telecom knowledge, I was contributing and doing a lot of Python coding, doing analysis for the data that originated from this from the setup. So it was not just I supervised. I literally did a lot of work on that. So actually, I'm really proud of that effort from at least from my perspective. Although I don't work on this project anymore. So again, this was probably my first and final Nature publication in my history as an academic. But who knows? Now, what is a quantum internet? We had a very interesting presentation from Cisco today about quantum networking, but maybe just recap what quantum networking is about. It's about secure communication, super secure communication, quantum computation in the cloud. This is what Cisco is mostly focusing on right now. Clock synchronization, super accurate clock synchronization, password identification, on pre-gaming, I would say. Probably this is the very far future about what quantum internet can offer, and of course connecting quantum computers in the big clusters. But the fundamental question that coming from this research was as follows: so how can we actually run such application on quantum network? The answer is it's not easy, as you have seen through all the presentations you've seen so far, because it requires a lot of interdisciplinary knowledge from people working in physics, people working in for programming languages, for theoretical physics, for algorithms, systems, you name it. I mean, almost every possible walk of science contributes to the knowledge of this system. So then, how to make it such a way that it's actually approachable to an average scientist. For example, so what the scientist should do? First of all, should run an application, right? From high-level software. I mean, because like, do you want to like program in quantum assembly? Probably not. It's made with Apple AI, but you want to make it in something just much easier for an average human. So that software also that needs to work on any quantum hardware. We've seen a less different types of quantum technologies that are out there. All of them have their own intrinsic properties. We don't want to understand how it's working. Then we just want to write the code for an application without it, right? And without knowing physics. I mean, I've heard the word 20 times from like, I'm not a quantum expert, you heard it also from me. So this is a very common feature of many people that have some relation to the quantum systems. That I'm not aware, at least, of anyone who will be able to be an expert in things coming from low-level physics up to application. It's practically impossible. I don't think that any human has capability to be an expert in that. So we need to kind of enable some scientists to have exactly that sort of So where do you run these? Anyway, this microphone again, it does work. It does work. It's amazing. So where do you run?
You took off the cable.
Yeah, probably actually, yeah. So I need to put it very close to my mouth. So where do you run these applications? We run them on like essentially on the end nodes, right? We should not care about what's happening in the network. And this is a service for us, and it delivers entanglement to the pairs of nodes, right? And what are these end nodes? Two types: photonic devices that prepare or measure qubits, and the processing nodes that perform the actions on the qubits has been received. So in a very influential paper, at least measuring a number of citations on that, where the concept of quantum internet has been proposed by Stephanie, David, and Ronald. So these are the three faculty from the QTech, from TU Delft. So they're trying to find out the mapping between the stage of quantum networking and examples of known applications. I will not read it out aloud. What is important here is that in that context, we need end nodes that can prepare and measure photonic clients. So they perform entanglement generation, prepare and measure qubit. End nodes that are quantum processors. So these are quantum computing systems. They should have few qubits that are fault tolerant, and should have also obviously have a quantum memory. So the post selection about prepare and measure should happen also a part of the quantum networking system, and the network itself needs to enable high-order entanglement generation. Okay, so these are the higher level components that quantum operating system should handle. So how does what does the network quantum application look like? So that's also a very high level description of that. So usually you have point-to-point communication, classical hardware and quantum hardware. What we call a classical in quantum is like classical is like that laptop, smartphones, like the classical computer science thing that operates and communicates with the outside world. And the quantum hardware is something that uses qubits to operate, right? The classical hardware is connected to the classical communication channel. In 99.9% of the cases, it's an optical link and a quantum hardware, which is also called the optical fiber through which the entanglement generation is being established, right? So abstracting this a bit, like the programmer of the quantum network application should just write a program for node A, and program for node A. He or she should not be even aware or bother what type of quantum hardware is there and what types of quantum hardware are there, considering the classical and quantum applications, right? So, and what is very important to see from a concept of quantum computation that the separate programs here are private, right? So like you can write separate programs for the node A and node B. So then abstracting this also a bit higher on the semi operating system level, the program on node A is composed of the quantum and the classical blocks, and they have to interact with each other. So the quantum program sends, for example, measurement request, measurement outcome, tells whether the entanglement has been a success or failure, and it's being passed to the classical channel and then passed on to the quantum, and so on and so forth. So you have a lot of interaction between the classical and quantum part. So the aim of this operating system is to enable this complete transparency and actually this like transparency from the programmer, not to bother about making sure that certain order of operations is enabled, that certain amount of operations requiring and connecting to a certain layer is done. We should, as programmers, not bother about this at all. Right? So again, what's different from the quantum computation is interactive, classical quantum execution of business programs. Right? That's what the differs computation. So let's go step by step for again high-level example of an example program that runs on a quantum network, and it's going to be secure delegated computation. So step one, first we need to establish a classical connection and processing. Then this goes to the quantum hardware to create a diagonal width server within a single, still within client side. Then I'm measuring my qubit. I'm sending the result of the measurement back to the classical part of my node, and then I'm sending that message on the classical channel with the measurement output to the other side through the classical hardware. Then the classical hardware passes on to the node B to the quantum part, so executing quantum gates depending on the message being sent across. Measure qubit, then send back the outcome of the measurement back to the quantum hardware. Send it back to the quantum channel, to the classical channel, back to the node B, and that's it, right? So you see that on a high level, we've seen at least 9 different messages being passed back and forth through classical and quantum hardware, and also in between node A and node B. So we wanted to, through making this operating system possible, separate that process from writing a program. The operating system, just like a classical operating system, abstract these processes from the end user. So let's look at actually running this application from 2 parts. Let's look at the network itself. So how does the entanglement generation stage looks like? So again, it's let's look at the point-to-point link, program A and program B, 2 users connected to the quantum network. Program A should make entanglement and measure, repeating it n times, and the program B should do exactly the same process. And examples, a couple of examples of the of applications that case are device-independent quantum key distribution, secure multi-party computation, and non-locally based applications, and many others. The links are here, but I'm pretty sure they're going to be downloading them right now. Trust me that there are many examples that perform examples of applications that run on that system, right? So to be able to run such an application, what we need exactly in our view, a quantum network stack which runs on top of the classical of the quantum hardware that performs exactly this operation. Now, this is very important here that we assume that in any quantum network realization, we need to have a central controller that is responsible mostly for orchestrating one of these at which points of time messages can be sent in between, and enabling very high percentage synchronization between every node and another. So that's very fundamentally different from a classical network where you don't have to a certain extent, a central clock or central controller that guarantees at which points in time these things are done. So reaching to the point of demonstrating quantum operating system application execution took a bit of an effort and some intermediate publications. So mapping this network architecture into the network stack, what we proposed in our ACM SICO publication from 2019 in Beijing, which I also was part of, mapping this classical OSI stack in a quantum OSI stack. We have a physical layer, which is which is basically composed of physical of a classical and quantum of a link. Classical network link layer, classical network layer, classical transport layer, and the application. So these yellow shaded blocks are the classical ones, as you see in any classical network. However, the physical one is what differs networking from quantum networking. We need to have that quantum block to operate on in the network. So the SIGMA publication dwelt on establishing that transparent classical versus quantum link. And the Connex publication, I wasn't part of this publication, was looking at the higher level aspects. So what services and should link the network layer provide? So first of all, you should need to create a qubit, measure it, and respond back with the information. It should be happening automatically on both sides of the chain between node A and node B. So higher layer to link layer asks for about, I want to have this many pairs per this many units of time. I want to have minimum level of fidelity that I'm expecting from you to deliver. That's the maximum waiting time I'm just accepting to wait until my qubits are generated. Then link layer to the higher layers should respond about, okay, whether it's okay or it's a failure on these requests that being established. You should provide me my entanglement ID, my qubit ID, and fidelity estimated, many other metrics. So essentially, in our approach, we're mapping all the classical OSI message translation from different layers into the quantum setting, right? So I'm going to show you at the end of the presentation the core results of the paper. So this is not being simulated by any means; it's being actually run on an actual quantum setup. So the quantum setup, the quantum networking setup, is available in Delft based on the nitrogen latency.
That's what just to talk about.
Yes, exactly. Yeah.
You showed in there.
Yes, I mean, the good question. Who's developing these diamonds? I wouldn't know. Definitely not Delft. I'm pretty sure there's someone else delivering this for them. And I also know that it requires an effort to actually chop these diamonds to an actual angle to get them right. So it's so that's what I'm saying. So I was just going back to our discussion. It's making this component actually accessible for someone on a just on sort of like Amazon way level. I want to have my nitrogen latency environment, but that would be an eye opener and really democratize that.
Temperature.
But that's no, I don't think it's a room temperature here. Yeah, it's a pretty loud setup, I would say. For those of you who have ever been to a quantum lab, the classical noise that you have, this sort of like this pumping noise from that stabilized the temperature for the phase stabilizer. So it's a big deal. But again, I'm absolutely no expert in that. Just like this is the physical layer qubits technology was used for that setup. So the setup was being used in QDAF. It's a system composed of two qubits, communication qubit and storage qubit, two nodes in a three-node network. So there was one intermediate node connecting with two links. More information about it was published in Science paper in 2021. I wasn't part of this paper. So this is like an example photo of such a setup. So there are many articles published about it because making actually the physical setup for the quantum network, it's a research of itself. I believe that one setup of three nodes costs more than €1 million. It requires at least 5 or 6 people operating in the background to keep it operational. It's as you know, like every day starts with resynchronizing the setup, measuring all the qubits are on a proper fidelity, and there's a lot of manual labor, a lot of manual control out there. Like thousands of parameters need to be controlled to make the setup work. So it's a very, very, very fragile system to make it work. So, like I said, to be able to establish the entanglement, the enablements needs to be super strictly synchronized with each other. We're talking about almost like a nanosecond accuracy personalization to have it entangled. So in my opinion, there is still a bit of a long way to go to make it really distributed and long distance network, because even on the synchronization side, we require a lot of research to make it accessible for the other students. So in experimental realization of our network, again running on the actual physical hardware, we have two programs, program A and program B, just mapping it from one by one. So one by one on the network side. So first of all, we have an application. Entangle, gate, and measure. So for them, this is the fundamental application operation that are out there. Then you're passed to our hardware independent stack, which is our network controller, which interacts with the hardware abstraction layer, which then interacts with I can just go maybe just later on. So on top of that, we have a center controller that coordinates interaction between these devices. So denotes request demands to the center controller, and the transfers are being sent back to the network. So then going back to the hardware abstraction layer, so that hardware abstraction layer has a programmed communication routines that are specifically tailored towards physical and quantum hardware that's operating for that. So this means that what we need to have for our quantum operating system to work is that hardware independent layer with different hardware abstractions layer prepared for different types of qubits. The hardware abstraction layer in our setup is simply connected to the SPI, and I mean it looks very fancy about the physical layer, but this is our friend AWG. That's doing all the control, and the only interface that was accessible for us was actually SPI interface. So 1980s technology is still quite prevailing in the 21st century quantum setup. So I mean, I'm going to spare you the details, but like that's lots of text, and just like on the high level, that's what you can see. This is actually the core thing. That's this way we're abstracting the physical abstract aspects of quantum setup to our quantum systems to work on. And first experiments from interacting on the physical layer with our quantum network. These are two examples of experiments from SIGCOMM paper. We are automatically requesting our quantum network to change a different modality that we have almost linear relationship between what we expected and what we got. So it's on a control level, we got what we wanted. Very important result, and I think was very, very important to understand where should we just focus our attention, is that where the most latency of the overhead comes from for the function of the cost fidelity. And as it is kind of like obvious and not surprising that majority of the overhead comes from the physical layer, and the protocol level side is only just a fraction of it, with a very, very little overhead compared to physical layer one. So again, we should still focus mostly on making sure that the latency caused by the physical layer to be significantly reduced. The interface layer overhead is only visible in the case when the fidelity is reaching almost a perfect one, because this really requires a lot of requests for reaching the desired fidelity. So again, our protocol layer overhead, which indeed there is a certain overhead involved, is still a fraction of what the overhead is composed to the physical layer. So now let's move on to part two about running an actual application on our processing nodes. So let's go back to our graph, the same setup to users. And now what we want to do, we want to execute program A and B, which is simply a sequence of classical and quantum blocks that we want to execute one by one. And we want to repeat it also n times. And examples of such system in which we're executing these sequences is like one blind quantum computation, same easy communication, different types of Byzantine agreements. So they sound, and they're still unfortunately a bit of a theoretical concepts. They prove that a complete different structure of a program that requires this independent execution of sequences is actually absolutely present in our operating system, and any operating system for that matter should also enable these types of applications. So on top of that, we also need to have a software stack, right, that executes exactly this different sequence. So state of the art, no such system existed, of course. Quantum computing, of course, very important. Many proposals. There are several instruction architectures present. There was a paper from Delft in 2017 published at IEEE Micro on that. There are already papers about networking from us out there, but nobody actually did exactly what I show in this graph. That you have an application level software stack and physical layer integrated in one system whatsoever, right? So none of this was possible before, right? So quantum Delta operating system, a high-level programming for a system that allows to execute literally a Python program and running this on your quantum setup. Has been executed in 2 locations in Delft using the Native Vacancy Centers and with the different types of qubits, which are ion traps, which are used mostly by the group in Innsbruck. We are the first one actually which demonstrated multitasking on a quantum setup. So it's not like a linear execution, so that multiple users running different types of programs can execute it all at once. And we managed to realize it on an actual setup. So to be able to do it, there are plenty of design considerations. So how to make it interactive between classical and quantum. We have to take into account different hardware profiles. I mentioned this already. We need to talk about timescales because on a different level, you require different level of accuracy of synchronization out there. They don't interact with each other quite well. You have to take into account, of course, the memory lifetime, because it's not like you have one bit that goes forever. The qubits have a lifetime of hundreds of milliseconds at most, with different fidelities that also fluctuate and change over time. You need to enable the interaction between the local and remote operators, and of course multitasking, because you want to have a network. You want to have different users enabled to operate on network at the same time. So on a high level, our architecture is composed of the QNode OS, which is simply a regular program, regular computer, classical network processing unit for that matter, that interacts through the NetCasm interface, which is another assembly language for quantum operations, also published by a group of Stephanie, which then passes on the quantum network processing unit, which performs other types of applications. Sorry, guys, I'm not gonna just go through that because it's 5 p.m. and he's probably gonna go home. I highly recommend looking at the quantum in our Nature, and Becky talks about it more. But on a high level, we need to execute these subroutines, which are executed in a NetCasm, which is a network version of quantum assembly language. But the quantum assembly language is a assembly language for quantum systems, not public to us. There's an extension of this into the networking applications, which are later on executed on the classical, on the quantum hardware in the architecture that was proposed before, right? So that glue that goes through quantum assembly subroutines to the physical instruction, that's what in the high level what our operating system wants to do. So we evaluated some of these programs on actual testbeds with 2 nodes, client and server, 1 qubit each. Both of those were actually had the QNOS implemented. So what we evaluated entanglement generation, gate execution, delegated computation, and multi-testing. So execution of delegated computation. So this is an example of a quantum case that we wanted to execute on that what the client wanted. So this was then mapped into different subroutines on the server and the client. And then we got the result showing that our system is executing exactly step by step, one by one, these tasks that you wanted to execute. So what you see here, this is what the programmer written. And that's it in any high level programming language you wanted to, and translation to all the routines and making sure of that this order of this operation have been executed has been done by the quantum QNOS system. Now, this is probably the most important result of the whole paper. So how does the delay or the latencies of each of these operations look at the client and server side? So on the client side, so the yellow one in this case is this EPR per success until client finishes. The gray ones is simply the latency of the translation from yes.
So your client server probably classically very.
Yes,
Right.
absolutely. Yes, yeah.
Wait time is a few minutes.
Absolutely. Very good, very good. Like, this is all a lab setup. This is not between Den Haag or no, absolutely not. This is the next step, and I'm pretty sure this is like where the most of the money is going to right now to
I
demonstrate it.
think
but it's
if
not-
they're different cities, then it's gonna be a challenge to keep the lifetime.
Yes, exactly. Yeah, absolutely. Yes. So spot on. Huh? So then looking at the server side, most of the delay is coming from the waiting for classifying, waiting for the preparation of the qubit and then measuring it whatsoever. So we see what's a good advantage of that system that our QNOD OS is able to push through API. I mean, this was this is my task. I should get it work. Write down for the user which part of the application had a certain delay to perform a statistics of which are later used for the application for the optimization of the system. So then we had another example, the multitasking, so local tomography on the client. So again, I'm not gonna just because it requires a lot of mental energy to process these graphs. I'm gonna spend them for you. But what's important is to show is that within the context of multitasking, we're actually obtaining much higher utilization of our resources compared to the system without multitasking, just considering different number of applications being running around. So again, there are some caveats in there. This is actually, in my opinion, not 100% yes.
So when you say utilization Q devices, your precious resources, the qubits.
Exactly, yes.
Try to keep
Yes.
the qubits between multiple applications.
I think it's mostly measured and also time that the system was idle and not doing anything.
Okay.
I think that's how it was measured. And was it measured on the level of a qubit? Was it measured on the level and
On the high level, you have let's say two applications
Yes.
running the platform, but the two applications you can share is two qubits, right? So
Exactly.
They're gonna
Exactly.
examine them in one way.
Exactly.
the application.
Yes. Because that's how the internet started. Like you have one mainframe computer which most
Right,
people
right,
want to
right.
connect with, and that's what we wanted to do here. So our postulate here in that paper is to enable widespread use of quantum internet, you need to have that fundamental functionality implemented for this to actually work and grow. So that's just the first example of what we can do. So there are multiple research challenges for like multi-node, as you see, like point-to-point length. What happens when you have 100 types of qubits that work here? Then had a perfect example. What about the time sensitivity? What happens when the delays, like on the classical link, becoming more stringent or larger? What happens that when your qubit generations exceeded and what you can accept? What happens when you have a different levels of fidelity on different nodes? I mean, there are tons of things that have to be still explored. So the work is ongoing. I know that Stephanie is working on a follow-up on QNOD that's called Koala, which has more features. I'm going to simply just spare you the details. There is a paper on that. If you just Google Koala, you're going to have all the information. And by the way, I saw the QBlocks out there. This is a startup company that actually just originated from research at UDEL. So they're probably one of the biggest companies, actually, the spin-off from Quebec Research in the past couple of years. So if you want to get more, I highly recommend sending an email to that address. We're looking forward for people cooperating on that topic. We have also our own quantum network simulator called NetSquid, which is actually being used also in the US. I know that folks from US are using this program extensively. And we have, I don't, but people at CUTA have lots of open positions for software engineers, PhD postdocs. They sit on a pile of money. So maybe next week after the Senate notification, who knows? You're more than welcome. So with all that, thank you so much. It was a pleasure. And well, if you have any questions, I hope we could answer them. Thank you.
It's time for questions.
I already answered my question.
Good job. Thank you.
I still have.
Yes.
So, regarding the synchronization, you mentioned whenever, none of it. So, what was the difference and, how that link to the different, platform on different sides?
The protocol that are using for synchronization is called the White Rabbit protocol. I think that's what they're using, and that's how much I know about the synchronization system that are using. Okay, hey, then have a nice and thank you so much for Okay, thank you. Okay, bye-bye.
Thank you so much. Great work.
Thank you, bye.
My understanding for variability is it's capable to be 400 something picosecond. So sounds like do you don't need that or?
I won't be able to answer that question. No, it's a verb. It's I don't know.
Right. The other part is just not talking about the multitasking. So I don't understand that multitasking is that basically kind of every quantum circuit is kind of between the multitasking is every quantum circuit ended or
Yeah. So what we're doing is like intermingling individual quantum operations like measurements, readout. Spread throughout time for different applications. So you're executing individual physical functions or steps on qubit, but they belong to different programs. So instead of just one program being executed first and only after it's completely executed and goes to it, we intermingle individual NAT-QASM steps, allowing it to squeeze them in a shorter period of time.
So this is assuming each circuit, each program is actually consists of multiple small things you
Yes,
can chop it off.
exactly. Yes.
If you really have a error corrected circuit, you really need to run that much long. You have no way to store it.
Absolutely. So then the advantage of multitasking will be very, very low. I agree. Yeah.
Okay, thank you.
I have a question about clock synchronization in your system. So, do you care both the clock offset and skewness, or mainly focus on the offset?
I will just.
Let me unmute myself here.
I think my question is like in your clock synchronization of a network, is the clock offset mainly your focus, or including both offset and skewness? Also, could you unmute yourself because I cannot hear?
Oh, yes. Can you hear me now?
Oh, yes. Thank you.
Thank you. You know, it's a very good question, but this was, I must answer, I don't know, because this was done by people setting up the quantum network, and also from a practical point of view, this setup is used by other groups doing non-quantum operating system stuff, and they are doing all the settings. I was not aware and part of that what you are doing. So if you have that question, I highly recommend sending an email to people that's working on that. I mean, just exactly this one. Yeah.
Okay. Thank you. Thank you.
Welcome. Yeah. So there are no. Thank you so much. Thank you. And thank you. Thank you.
Thank you very much. And with that, our workshop comes to an end. Thank you everyone who gave a talk, and thank you everyone for attending. And hopefully we'll see you all next year. Thank you.
Thank you.
Thank you so much, everyone. Looking forward to see everyone next year.
Thank you so much. Bye-bye.
Thank you.
Bye.
Bye-bye.
Bye.